In this lecture, we'll continue with our discussion of probability rules, but we'll begin with identifying a concept called conditional probability. Before watching this lecture, you may want to return to Canvas and watch the interactive demonstration of conditional probability, which will provide you with a visual description of this concept. This is sometimes a difficult concept for people to grasp because it's a little bit different than a traditional probability. It also is very, very similar to what we're going to discuss in terms of an intersection probability. So making sure that you can clarify when and how to apply conditional probability is important. So we have an additional resource just to help you get a better grasp and a more intuitive understanding of what's happening with conditional probability. All of that said, we're going to define the term here. And the conditional probability of A, given that B has occurred, from a mathematical sense, is just the probability that both A and B have occurred divided by the probability of B. So let's get some notation out of the way here. First of all, from a notational perspective, the probability of A with the bar underneath it and then B. So here we see the probability of A given B. That probability, the way we read that, is the probability of A. This bar in the middle is read as given that B happened. The idea behind conditional probability is that we have two events, A and B, and we know that potentially A could occur or B could occur. And we're interested now in just the scenario where B has occurred. So we know that B has occurred. Given that B has occurred, now what's the likelihood that A also occurs as well? So we've changed our basis. If I just said, what's the probability that event A occurs, right? The probability of A, then we would look at all of the information here in A out of the entire sample space. But now, suppose I tell you instead, what's the probability that A occurs given that B has occurred? Now I've established the fact that we know that we're in the scenario where event B has happened. So our basis has changed. We're no longer looking at the entire sample space. We're only interested in the event that B has happened. And so now the likelihood that A occurs given that B has occurred is just this part here in the overlap, right? So it's the probability of A intersect B divided by our new basis, which is the probability that B has happened. Right, so that's the idea here. So for example, if I ask you, what is the probability that you're going to be late to work tomorrow? You would kind of have an idea of the percentage of time you're late for work. Maybe it's 1% of the time. But if I said, given that there is a wreck on the interstate highway, what's the probability that you're going to be late to work? Well, now that probability changes because that additional information, the fact that there's a wreck on the interstate highway, updates the likelihood that you're going to be late, right? In this particular case, it probably increases the likelihood that you're going to be late. I know for my commute, if I encounter a wreck on the interstate highway, almost always that puts me 5 or 10 minutes late to work. So it's that idea of changing our basis. We're no longer looking at one event out of the entire sample space. We're narrowing our universe down to just the situation where B has occurred. And now, given that we know we're in that scenario, how likely it is that A occurs as well. So here's an example. We have a large bank. We know that 6% of the employees are computer programmers. We know that 50% of the employees are female and 2% of the employees are female computer programmers. If a female employee is selected at random, what's the probability that that employee is a computer programmer? Okay, so the question here is not, if I go and randomly select a single individual from the bank, how likely is it that that individual is a computer programmer? Now we're saying I'm only going to look at female employees. I'm going to go and select a female employee, and given that we have a female employee, now how likely is it that that individual is a computer programmer? This is different from the 2% that we have here. This 2% says out of all of the employees, if I select an employee at random, 2% are both females, right, and computer programmers. So this is a joint probability females and computer programmers. What we're asking for here in this first question is a conditional probability. Okay, so the language is a bit subtle. Oftentimes, if you're talking about a conditional probability, you'll have the word given like we do in this second scenario here, but sometimes you just have subsetting language that is indicative of conditioning. For example, here we just have if a female employee is selected, right? We're not selecting an employee at random, but if we select a female employee, what's that probability? Okay, so how would we work this problem? Well, again, the way we start and attack a probability problem is to write down what we know. So we know that 6% of the employees at the bank are programmers, 50% are females, and as I mentioned before, 2% are female programmers. So they're both female and they're programmers. And our first question, if a female employee is selected at random, what's the probability that the employee is a computer programmer? So in these conditional probabilities, the thing that we are conditioning on, the given part, the subset part, goes on the right-hand side of this bar. So in this case, that is the idea that an employee is a female. And the probability that we want to compute goes on the left-hand side. So we want to know, given that an employee is a female, what's the probability that that person is a programmer? Okay? Our formula tells us that this is just the probability of being a programmer and being a female, divided by the thing that we're conditioning on. Okay, so the thing that goes in the denominator is the thing that's on the right-hand side of this bar. So divided by the probability of being a female. And if we plug those numbers in, the probability of being both a programmer and a female is 0.02. Probability of being a female is 0.5. And so our probability here is 4%. So given that you have a female employee, if you selected a female employee at random, the probability that that individual would also be a computer programmer is about 4%. We could also ask kind of the converse question, given that an employee is a computer programmer, what is the probability that that employee is a female? Well, in this case, the thing that we're given, right, the thing that goes on the right-hand side of this bar is the fact that an employee is a computer programmer. So in this case, our given piece of information is that the individual is a programmer. What we want to know is, given that information, what's the probability that that individual is also a female? So again, we apply our probability rule. The probability of A given B is just the probability of A and B divided by the probability of B. So here is the probability of being a programmer and a female divided by the thing on the right-hand side of the bar, so divided by the probability of being a programmer. So if we plug those numbers in, 2% are females and programmers, 6% are programmers, and if we do that math, that comes out to be about a third, 0.33. So that's how we do this conditional probability. Recognizing that you're in a conditional probability situation requires carefully reading the language to recognize phrases that would indicate we are subsetting our population, and then we want to be sure that we correctly write down the representation of the probability, which will lead us to the correct application of the formula. A closely related concept to conditional probability is the concept of independence. If two events A and B occur, these two events are independent if knowing that B occurs has no influence on whether or not A occurs. So in other words, if I tell you that event B has happened, it has no bearing on the likelihood that event A has happened. This is a silly example, but one that I like to use. Suppose that it's raining outside, and suppose that I have brown hair. I could ask, what's the probability that I have brown hair and it's raining outside? Those two things can happen at the same time. But if I told you my hair is brown, so given that I'm an individual with brown hair, how likely is it that it's going to rain today? Knowing that my hair is brown gives you no useful information on whether or not it's going to rain today. My hair being brown and raining today are independent events. Knowing that one happens has absolutely no influence on whether or not the other one happens. Contrast that with the example that I gave with respect to having an accident on the interstate highway. If I tell you that there's an accident on the interstate highway and then I ask you the probability that you're going to be late to work, knowing that additional piece of information changes the likelihood that you're going to be late to work. So those two events, being late to work and an accident on the interstate highway, those are not independent events. So it's this idea of, does knowing one event, does knowing that one event occurs somehow change or influence the probability that a second event occurs? If they do influence each other, then they are not independent. If they do not influence each other, then they are independent. And so the way that we check for this condition is we ask, is the probability that A happens given that B happens just equal to the probability of A? Or equivalently, is knowing that A happens, the probability of B given that A happens, is that just the probability of B? If this equality holds, then these two events are independent. So in this case, if I knew that the probability of rain was 20%, and I told you that I had brown hair, the probability that it rains given that I have brown hair would just be 20%. Those events would be independent of each other. So let's look at an example. Right, let's continue with our computer programming example. We might ask, are being a computer programmer and being a female independent events? Right? We might want to know that information. So the way we would check that information is we would say, well, what's the probability of being a programmer? And what's the probability of being a programmer given that you're a female? If those two are the same, if knowing that I'm a female does not change the likelihood that I'm a programmer, then those would be independent events. If they're different, then that suggests that being a female changes the likelihood of being a programmer. So we know the probability of being a programmer, that was 0.06, that was given to us in the problem. The probability of being a programmer given that you're a female was 0.04. We computed that in a previous question. And so the question is, are these two things equal? And in fact, in this situation, they're not. So being a programmer and being a female, these two events are not independent. Another example, just referring back to the previous lecture, we looked at this idea of a household being prosperous and a household being educated. And so in this situation, you would hope that being educated and being prosperous are somehow related to each other. If I've spent the time and money to complete my college education, to get my MSBA degree, then hopefully that's going to have some influence on my prosperity in the future. That's part of the motivation for most people for going to college. And so if we wanted to answer that question, we would need to know what's the probability that an individual is prosperous or that a household is prosperous, right? And is that different from the probability that a household is prosperous given that they're educated? So if I know that the household is an educated household, does that essentially increase the likelihood of being prosperous or not? That's really what I'm asking when I ask about independence. In this case, the probability of being prosperous, we were told, is 0.125, and we computed the probability of prosperous given that you're educated in the previous example, and that turned out to be 0.325. Okay, so again, these two things are not equal. You're about 3 times more likely to be prosperous if you're educated than if you're not. And so these two events, again, are not independent. So I would caution you, if you're trying to determine whether or not two events are independent, don't just let your intuition take you there. Your intuition may take you to the wrong place. It may lead you to the wrong answer. But from a statistical perspective, from a mathematical perspective, if you check this condition, then you can always have a solid objective basis for determining independence. So if the question refers to independence, you need to look at the probability of A, and the probability of A given B, and determine whether or not those two things are equal before you move on. We need to establish the concept of independence because not only is it related to conditional probability, it's also related to the probability of a joint event occurring. So for any two events A and B, the probability of A given B, right, the probability that both A and B occurs, that's just the probability of A given B times the probability of B. So again, what we're talking about here is if we have two events A and B, we're talking about this overlap. Okay, so what's the probability that both A and B occur? It turns out that that probability is just the conditional probability of A given B times the probability of B. And again, notice the thing that we're conditioning on is the thing that we're multiplying by. So this and this are the same. If we know that two events A and B are independent, then we can actually simplify our computation. We can just multiply the probabilities. And if you think about it, if we apply independence, independence tells us that the probability of A given B is just equal to the probability of A. So we can make that simplifying assumption, and if two events A and B are independent, then we can simply multiply their probabilities to get the joint probability that both A and B occur at the same time. Another example, 52% of all U.S. adults are women. Out of all U.S. women, 44% suffer from holiday depression, and we want to know what is the probability that just a randomly selected U.S. woman a randomly selected U.S. adult is a woman who suffers from holiday depression. So let's take a look at a couple of examples. First of all, suppose that we have a scenario where we're looking at holiday depression and we want to understand how that's related to a person's gender. So we're told in this example that the probability of an individual being a woman is 52%. We're told that out of all U.S. women, 44% suffer from holiday depression, and we want to know the probability that a randomly selected U.S. adult is a woman who suffers from holiday depression. So the trick here is understanding whether we're talking about a conditional probability or whether we're talking about a joint probability. The first thing that we're given is out of all U.S. women, 44% suffer from holiday depression. So this terminology, out of all U.S. women, this is subsetting language. You could say, in other words, given that an individual is a woman, 44% of those individuals suffer from holiday depression. So that particular statement is actually a conditional probability that says, out of all U.S. women, given that someone is a woman, there's a 44% chance that that individual suffers from holiday depression. Now, the second question says we're going to randomly select a person, randomly select an adult from all of the population of the United States, and we want to know the likelihood that that individual is a woman who suffers from holiday depression. Or in other words, what's the probability that that individual is a woman and they suffer from holiday depression? In that case, we're selecting from the entire population. We're not selecting from a subset. So that second phrase there, the question that's being asked, is for a joint probability. If we apply our rule, that's just the probability that an individual suffers from holiday depression given that they're a woman, times the probability of the thing on the right-hand side times the probability that they're a woman. And so that comes out to be 0.44 times 0.52, and that gives us a probability of 0.229. So the language here is very important. Are we selecting from a subgroup? Are we selecting from the entire population? And that helps us sort out which probability is in play. Another example here, according to the Open Doors report, 9.5% of full-time U.S. undergrad students study abroad. 60% of the undergrads who study abroad are female, and 49% who do not study abroad are female. And we want to know what's the probability that a randomly selected, again, we're going to randomly select a student out of the entire U.S. undergraduate population. What's the probability that a randomly selected student is a female who studies abroad? Okay, so let's compute the probability. Again, we're asking about the probability that a randomly selected student is a female who studies abroad. So this is a joint probability. We're asking out of the entire population, how likely is it that a student is a female, and we could read this as and, the female and that individual studies abroad. Okay, so our basic law of multiplication would tell us that the probability of A and B is just the probability of A given B times the probability of B. That's our law of multiplication. We have all of the pieces we need here. So the probability that an individual is a female and they study abroad is just the probability that the individual is a female given that they study abroad times the probability that they study abroad. Right? We have all of that information. So this is 0.6 times the probability of studying abroad is 0.095. And if we do that multiplication, it comes out to be 0.057. So about 5.7% of undergraduate students are females who are studying abroad. So all of these concepts, conditional probability, independence, and the multiplication rule or joint probabilities, all kind of work together to provide us with a complete sense of how to compute these sorts of probabilities. The last topic that we need to cover is the topic of contingency tables, and that will be the subject of the next lecture.